Welcome back to Course 212. In this lecture, we are going to talk about stackless tree traversals as well as threaded binary trees. So let's quickly pick up where we left off last time. A quick reminder of what we covered. In the previous lecture, we have started to discuss the tree abstract data type, and we have discussed binary trees in detail. So binary trees, specifically binary search trees that we are going to be working with quite a bit this semester, are essentially data structures that can be thought of as linked lists that branch out in two directions. Specifically, every single node will not just have a single next pointer, but rather would have two pointers, a left pointer and a right pointer, where the left pointer would lead you to the left subtree and the right pointer would lead you to the right subtree. For a binary tree to be called a binary search tree, the following two properties must hold. All values in the left subtree of any node must store values smaller than the value stored in that node, and all values in the right subtree of a node should store values larger than the value in that node. And like I have already mentioned, I think every single subtree of any single node should also be a BST, in other words, should adhere to the same rules. So in my example, 5 is the root of the tree. It has two branches, the left branch, left subtree, and the right branch, the right subtree. And if you consider just the subtrees, 3 and a 1 also stick to this relationship. 1 is smaller than 3, therefore it's on the left-hand side of 3 and not on the right-hand side. Why are we interested in this data structure? Well, because if your tree is balanced, in other words, if the size of the left branch is more or less the same size as the right branch, then it can be very, very efficiently searchable. Efficiency of the search is logarithmic, which is very good. We have also covered some traversals last time. A traversal is simply an algorithm that allows you to visit every single node in the tree, so visit the entire data structure. And we have covered breadth first, where you visit the tree layer by layer, starting with the roots, as well as depth first. The idea of depth first is that you choose a branch, then you go as deep down that branch as you can before you move on to the next branch. The especially useful depth first traversal that we have discussed was the in-order traversal. It's useful in the sense that if you print values as the in-order traversal visits them, they will actually come out in ascending order. And the idea is quite simple. If you have a tree, first visit its entire left subtree, then the root, then the entire right subtree, and recursively apply the very same algorithm to every single subtree. So we have also looked at the code for the various depth-first traversals, and for the in-order traversal, the code is as simple as 4 lines of code. We have an if statement, 2 recursive function calls, and 1 visit, which is just a placeholder function, can be replaced by a print function or, maybe some other function. Essentially, this is the place where you actually access the value of every single node once. Okay, great. So this is a short summary of last lecture. So how are we going to expand on this knowledge in this lecture? Where are we going to take this? Well, here are the 3 depth-first traversals. And the nice thing about depth-first traversals, if you remember from last class, breadth-first traversal actually made use of a queue to accomplish this layer-by-layer visitation of the nodes. With depth-first, it's only 4 lines of code, whether you want to do pre-order or in order or post-order. 4 lines of code is obviously very, very little, so this code is extremely elegant. And it doesn't look like we need to use an external data structure such as a queue to accomplish our goals. So here is a question. Sure, these algorithms are elegant, as in they are minimal. Just 4 lines of code. You can't write any shorter function than this to traverse the entire complex data structure. But are they efficient? Let's discuss that. Let's look what actually happens when the recursive function is called. And for my recursive example, I'm going to use the post-order traversal as just for the sake of the example. Remember, what happens when recursive function calls are actually called. Recursion is not just this magical thing that happens. To perform recursive function calls, you actually need to push subsequent function calls onto something known as the system stack. So you are not explicitly using a stack in your code, but behind the scenes, in order for the function to be able to call itself multiple times, it actually has to save its own states on the system stack so that backtracking can happen when the time is right. So in this case, we start by calling the post order function on 5. So this function call is pushed onto the system stack. And 5 is going to remain there until this function call returns. But obviously 5 cannot simply return. It can't just exit. It has to first call itself on the left branch and then on the right branch, then visit P, only then will this function code be done. So 5 has been pushed onto the system stack. We're now going to the left sub branch, which would be this branch here. So next up, 3 is going to be pushed onto the stack. Post order P left is 3, so we are now again inside of this function. The second instance of the function is pushed onto the system stack. Similarly, 3 can't just do its own thing. It actually has to call the function on its left and right child. So it will call the function on 1, which is its left child. We already have 3 function instances on the system stack. What is 1 going to do? 1 is actually going to attempt to call itself to call the function on its left and right child, but it doesn't have a left or a right child, so it will push a null onto the system stack, and that would actually cause the recursive function to reach its base case. You only answer the if statement if P is not null, so when 1 tries to send it its left child, this if will finally not yield true, and for the second child it will also not yield true, so both of the function calls will simply return, and then finally we will be done with 1. We will finally be able to pop it off the stack and backtrack to 3. Now, as you can see, I ran out of screen space. I didn't even visit everyone. So this is how many interactions with the system stack you have just to visit this guy here at the bottom. So yeah, in the code, this looks very, very elegant, but in reality, there is still another data structure doing the hard work for you. In this case, when I speak of efficiency, I do not necessarily refer to asymptotic complexity. In terms of the big O notation, every traversal would be of a linear complexity. In other words, big O of n. Why is that the case? Well, we have n items in the data structure. And if we want to traverse the data structure, obviously, every single element must be visited exactly once. So the number of elements will determine the number of visits, right? So no matter what traversal you pick, breadth first or depth first, complexity is still going to be linear. But the question is, how many, in terms of memory efficiency, how many extra memory locations do we actually require to accomplish our goal? So far we have determined that breadth first traversal uses an explicit queue, and the depth first traversal actually implicitly uses a stack. But both of these traversals rely on a secondary data structure to actually keep track of where you are in the tree. Okay, so clearly recursion works, but it uses a system stack. So can we somehow rewrite this function iteratively to avoid referring to the system stack? Well, try all you can, but I'm sure even the most genius programmer will come up with a solution that uses a stack in one way or the other. This is just one example of how this function can be rewritten iteratively. If you compare this code to the breadth first traversal, you will see that it is extremely similar. The only difference is we replace the queue with the stack. And if the queue is replaced with the stack, we will actually be able to accomplish the pre-order depth first traversal without coding it recursively. So it's all good and well. But are we really gaining anything? The code is a lot less elegant now. It's not 4 lines of code anymore. It's much bulkier, and it will take you longer to comprehend what exactly is happening. And also, we do not really gain much memory-wise because we are actually still using a stack. It's just that instead of using a system stack, we are now happily using an explicit stack that we have declared ourselves. So really, this doesn't make the function any more memory efficient. So in my opinion, the non-recursive implementation is not better by any means. Let's also see how other depth-first recursive functions can be rewritten iteratively. All of this code is available in the textbook, by the way. So it turns out that converting post order to apologies. Converting post order traversal to iterative code is actually a little bit more complex than pre-order. In this case, we still use a stack, and instead of a single while loop like in the previous slide, we actually have a while loop, and instead of that while loop, we wrap a for loop as well as another while loop. So the code gets progressively more complex. And if you ask me which one I prefer, well, hands down, it's the recursive variant. Both of them use a stack either implicitly or explicitly, so neither is better in terms of memory efficiency, but the second one is a lot harder to read and to understand, to explain to another programmer. And the readability of your code is actually quite an important property in the real world, where you work on a project together with other people, and no matter what code you write, you have to explain it to somebody else. Try and explain this one at the bottom, you'll probably need time just even to figure out what's going on here. And finally, my favorite, in inverted commas, is the conversion of the in order, in other words, the most useful depth-first traversal to iterative code. Here you are. Once again, we use the stack explicitly. We have a bunch of while loops wrapped inside each other, and in my opinion, this is almost as ugly as it gets. So once again, hands down, recursive function wins for me. If I was, as a programmer, to choose one implementation over the other, I would definitely much prefer the in order written recursively, just because I can clearly, intuitively understand what is going on here versus this iterative hell below. So, bottom line of these examples is just converting recursion to an iterative solution does not actually improve the efficiency at all, right? All you do is wreck the elegance of the solution. So perhaps this is not the way to go. Does it mean that recursion is the only option and using an implicit stack versus an explicit stack is the best we can do? Or can we actually somehow, in a smart way, come up with a traversal algorithm that completely dismisses the usage of the stack? So the question for today is, can we write a piece of code that traverses the tree efficiently? So linearly, it shouldn't take suddenly more time, but without using either an implicit or an explicit stack. Well, first of all, why do we even need a stack? Why are we so stuck on this idea of putting things on the stack? Well, clearly, we start at the root, right? And depth first implies that you have to go all the way down the branch on the left-hand side before you can go to the right-hand side. And the thing is, when you start at the root, you really do not know how far that branch extends. What is the depth? It's just like with a linked list. If you're given just a head, you don't necessarily know how many steps it's going to take you before you get to the place that you're looking for. So, if you want to go depth first, if you want to go all the way down until you find a leaf, you need a way to be able to backtrack. In other words, to retrace your steps and actually return all the way to the root, to the place where you started, to now, once you have finished with one branch, to go to the next branch of the tree, from left to right or right to left. So backtracking is really the reason that causes us to use a stack in one or another way. So, are there any other ways of backtracking besides using a stack? Usually, the first solution that the students propose in class when we discuss this in live lectures is, well, trees are clearly singly linked. 5 knows that 3 is its left child and 7 is its right child, but 3 does not know who its parent is and 7 does not know who its parent is. So maybe if, in addition to the left and the right, we also store the parent pointer, so you basically make the tree doubly linked, then you would be able to backtrack without using a stack. And that is actually very, very true. You can definitely do that. Question is, would that really be more memory efficient? Well, you will avoid using the stack. However, you will have to actually store double as much memory for your arcs, right? We won't just, it's almost like currently 5 knows the address of 3 and the address of 7, right? 3 doesn't know how to go back to 5, 7 also doesn't know that. But if we make the tree doubly linked, then essentially we will have 2 arcs connecting every 2 nodes. So we will use double as much memory to actually store all of those references. And also, if we backtrack using the links, the upward links, we will sort of be traveling down these paths twice, which might not necessarily be the most efficient way to travel. So it doesn't actually seem that simply making the tree doubly linked will solve our problems. And that is where a nice and intelligent compromise solution has been proposed. And the solution that we're going to discuss now is the threaded binary tree. So threaded binary tree is basically a binary search tree where some of the existing variables are reused in such a way to enable stackless in-order traversals. Why in order? Well, because in order, in fact, is the most useful traversal of a binary search tree. The reason for it is that it actually outputs the values in a sorted order from smallest to largest or largest to smallest, based on whether you start on the left branch or the right branch, right? That is what we are going to aim to emulate with threaded binary trees. Just a quick disclaimer. You can actually write threaded binary trees to emulate a post-order or a pre-order traversal instead. The only limitation is that you typically only choose one, pre-order, post-order, or in-order. And in my examples, I will only work with in-order because it's the most intuitive and the most useful one of the 3. Okay, so what we are going to do is, instead of storing a parent reference, we will actually store the reference to the next node that must be visited, right? So it's essentially, if we go back to the previous slide, if we move all the way down to 1, right, we will obviously print 1, 3, and 5 before we go to 7, but if the tree was doubly linked, then to backtrack from 1 to 5, we will basically have to go from 1 to 3 and from 3 back to 5. However, if you have already visited the entire left branch, then clearly climbing all the way back up the stairs step by step is a little bit inefficient. So it would be much nicer if we could go all the way down to 1, and then once 1 has been printed, and its parent has been printed and whatnot, we sort of want to be able to actually go straight back to 5 instead of maybe doing this step by step. But anyway, you'll see what I mean very soon. So we do not want to just store the reference to a parent. Instead, we want to store a reference to the next node that should be printed in the in-order traversal fashion. Whether it's a parent or a node further in the tree, it doesn't really matter. Also, what is very important, we are not going to declare an extra reference variable. Instead, we are going to reuse the left and right references, which are currently not used by specific nodes in the tree. For example, if you look at the leaves of the tree, the leaves have their left and right pointers declared, but both the left and the right are set to null because the leaf doesn't have any more children. Now, those null pointers can actually be set to useful addresses, and that is exactly what we are going to be doing with threaded trees. So, if you are at the leaf node, or at any node which doesn't have a left child, what you can do is make that pointer, instead of pointing to a non-existent left child, point to the in-order predecessor of this node in the tree. Similarly, if you find a node whose right pointer is null, So that can be a leaf node or just a non-terminal node which only has a left child. That right pointer, instead of just pointing to null, can be made to store a reference to the next value and the successor of this particular node in the in-order ordering of the tree. And these references we are going to refer to as the threads of the tree. Trees can be single-threaded or double-threaded. With single-threaded, you only use the right pointers, so you only enable traversal from left to right. With double-threaded trees, you are going to reuse both the left and the right pointers, and this allows you to go from smallest to largest, as well as from the largest to smallest. And in case this is the point where you are getting confused, let me quickly show you a picture to hopefully show what I mean, illustrate this idea. Okay, so the green tree right here is a single-threaded binary search tree. The arrows, solid arrows, are obviously my left and right pointers, and the dashed arrows are the threads. So 6 has a left and a right child, therefore it doesn't have any threads. 3 has a left and a right child, therefore it doesn't have any threads. 1, however, is a leaf node. It doesn't have any children to the left or to the right, so we're going to reuse this right pointer to make 1 point to its successor in the in-order traversal. Obviously, if we want to print everything in order, 1 should be followed by 3, followed by 5, followed by 6, etc. So 1 is going to store the address of 3. And yes, in this case, 1 actually points back to its parent. However, look at 5. So 1 stores the address of 3, but 3 doesn't attempt to store the address of 6. Instead, it just has 2 children, 1 and 5. So when we visit this left branch, we can print 1, use this dashed arrow to get to 3, print 3, use 3's right point to get to 5, print 5. So we have now printed the entire left branch. Now to backtrack to 6, we are not going to go from 5 back to 3. Instead, we will make 5 actually store the address of 6. So once we have printed the entire left subtree, we can make a hop and go straight to the root, straight to 6, who obviously has to be printed next. This tree below here is a double-threaded tree. The very same rules apply. The only difference is we store in characters here instead of numbers, but they also sorted in a binary search tree fashion. And the same thing here. C, for example, is its predecessor, doesn't store the address of D, not of its parents, but rather the value which precedes it, right? A, B, C. B is obviously the predecessor of C, so C points to its predecessor in this sorted traversal rather than to its parent. Or E, for example, points to its successor, once again not to its parents, but actually all the way to F. Great, hopefully the idea makes sense to you guys. In terms of the code, the modifications of the code are actually very, very minor. So like I have said, we are not going to declare an extra pointer variable. We are not going to store another object BST node. Instead, we will add a very simple small value. We will just store a boolean, so it's a true or a false. We'll call it hasThread, and that will tell us whether the current right pointer is actually a child. In that case, hasThread is going to be false, or if it's actually a thread that points upwards, in that case, hasThread is going to be set to true. This is for a single-threaded binary tree. If I was doing double-threaded, I would probably have 2 boolean variables, hasRightThread and hasLeftThread. And those 2 booleans will basically tell me, okay, the left and right are never allowed to be null, but when they are not null, what are we looking at? Is it a thread or is it a child? Does it go downwards or does it point upwards? All right, so let's see how this tree is actually can be efficiently traversed without a stack. Remember, the whole deal here is we want to code a traversal which doesn't use a stack at all, doesn't use any external data structures. Okay, so we're going to start at the root. And then, because we are doing depth first in order traversal, we're obviously not going to print the root. We want to start by printing the smallest value first. Therefore, we're going to go as left as possible, because clearly the leftmost node in the tree will be the smallest node in the tree. So we're going to keep going left until we find a node which doesn't have a left child, in other words, which is the leftmost leaf node of the tree. Then once there, we are going to start this while loop, and we will say, okay, so while this guy is not null, visit the current pointer. So we're going to visit 1, in other words, print 1, and then check if 1 actually has a right subtree. If any node that you're looking at has a right subtree, then you're going to go onto this right branch and find the leftmost child in that branch. Otherwise, if the value doesn't have a right child, then you know it has a thread instead, then you will simply follow the thread. So in this case, we go to the leftmost node, we are at 1, we print 1, so that's where the visitation happens. Then we're going to ask 1, all right, 1, do you have a right child? No, you do not. So we're going to just follow the thread instead. We end up in 3. We are back at the while loop. Obviously, we're going to print 3, then we're going to ask 3 if it has a right child. It does have a right child. We're going to go to the right, we're going to visit this right pointer, and inside of this right subtree, find the leftmost node. The thing is, 5 is the only node, so it is the leftmost node of the right branch of 3. We're going to print 5, and then we're going to follow 5's thread, taking us to 6. And so the process continues. But as you can see, there is no recursion involved. There is a single while loop that does the job for you, that traverses the entire tree. We did not use an external data structure. These couple of threads actually enabled us to go through the entire tree without any external memory storage. So memory-wise, this is actually pretty efficient. So this is all good and well. We have now determined that ordinary binary search trees either use an implicit or explicit stack for in-order traversals, for depth-first traversals, rather shall I say. Threaded BSTs do not use a stack, but they still maintain some extra variables, right? They still modify the original data structure. Yes, they do not use an external data structure, but you can't just use the good old standard BST and print everything without a stack. You need to modify it somehow to kind of preserve the stack order, in our case using threads. So second question for today is, can we actually manage to be smart enough to write an algorithm that does traverse BST without using a stack and without modifying the data structure? So without creating these extra Boolean variables, without storing any extra memory, without storing any extra data at all. And the question is, yes, you can actually do that. Let's consider a special case. Look at this tree on the right hand side. Is it a tree? Yes, it is. Is it a binary search tree? Yes, it is. It's not a very nice looking one. It is essentially a tree which only has one very, very long right branch, not a single left child. If you are given such a tree, would you be able to traverse it without threads and without a stack? Well, most definitely. You simply start at the top and then you go right until you reach the right pointer that is null. So you only take right turns and you just keep printing every single node that you encounter along the way. In fact, this traversal of a tree is the same as a traversal of a linked list, because a tree that only has right children is essentially a linked list, right? So in a very special case, if your tree is just a very, very long right branch, it looks like you can in fact traverse it with a very simple while loop with no extra bells or whistles. However, obviously, you know that trees do not look that way, right? Typically, you do have the left branch and the right branch, and you want to have both branches because branching out is what enables efficient search. So how is this really useful? Well, it turns out that it's useful if you manage to write an algorithm that actually linearizes the tree for you. So no matter what the shape of the tree is, you can write actually an algorithm. An algorithm was first proposed by Joseph Morris. It's an algorithm that basically takes a tree of an arbitrary shape, it converts it into a really, really long right branch, it prints it, and then at the end of the day, it also manages to put it back together. This traversal is known as the traversal through transformation. We will not be modifying the internal workings of the data structure, but we will be modifying the shape of the data structure along the way. Let's see how this works. Let's look at this interesting algorithm. Okay, so let's first do a very dumb approach that basically starts at the root and checks for every single node whether that node has a left branch, and if it does, it basically gets rid of the left branch. So let's look at what's happening here. We initialize our pointer p, which is going to be our current pointer, to the root. Then we're going to say, okay, while p is not null, first of all, check if p has a left child or not. If it does not have a left child, that's great news. Remember, we want the tree to be one very, very long right branch. So we do not want p to have left children. If it doesn't have a left children, great success. Print p, visit it, do whatever you want with it, and then go to the right. Carry on with your simple process of visiting all the kids on the right branch and ignoring all the lefties. Otherwise, however, if p does have a left branch, you can say, well, that is not really, doesn't sit well with me. I do not want left children. I want the tree to be one very, very long right branch because that makes traversals easy. So what I'm going to do is, I'm going to go to this left child. I'm going to find the rightmost node in that subtree to the left-hand side. And then I will make p the child of that rightmost node. In other words, in my example, you go left. Well, you discover that p does have a left child. You then go to the left subtree and you look for the rightmost node in that left subtree. The rightmost and the leftmost node is a. So what we are going to do is we are actually going to make d the child of a. We make p the right child of TMP's rightmost node. Great. Then we are going to set p to p's left, and given that d still remembers that a is its left child, that would actually take p all the way back to a. What have we done? Well, we've destroyed this tree. We basically have stretched it out into a single right branch. Now we can repeat the process. We will obviously ask, once p has moved, we will be at the top of the while loop. We will ask p if it still has left children. Well, not anymore, because a doesn't have left children, so it's great. We're going to print a and simply move to the right. Now we're pointing at d. We will ask if d has left children. It doesn't. So we're going to go print it and move to the right again. And then we're going to print e and be done with this algorithm. First of all, do we preserve the BST properties by making d the right child of a? Well, interestingly enough, we actually do. The rightmost child of the left branch will be a value that is the largest value in the left, but everything from this root to its right will actually be larger than that value. So the rightmost node of the left subtree is a perfect divider between the left and the right-hand side. So yes, placing d to the right-hand side of a is valid in terms of BST property. So this reconnection doesn't actually ruin the BST properties of the tree. However, there is still a bit of a problem with this current algorithm, and the problem is we totally wreck the tree in the process. We started with this nicely balanced tree where the length of the right branch was exactly the same as the length of the left branch, but by linearizing it, we've stretched it out into one massive linked list, and that is obviously not a great idea because this tree would not be efficient for search purposes anymore. So clearly, after you've stretched it out, you can't just leave it at that. You probably have to somehow put this tree back together into its original form. So let's modify this algorithm to actually allow us to traverse the tree and also make sure that it comes back to its original shape once we are done with it. Here is the modification of the algorithm you saw on the previous slide, and this is the actual algorithm that Morris has proposed. It's known as a reversible Morris traversal, and yes, this is a traversal of the tree by transformation. We will be changing the left and the right children along the way, but at the end of the day, everything will fall back in place. Okay, so once again, I'm going to show you an example on the teeniest tree possible, And once you've grasped how this works, we're going to also do an example on a slightly larger tree to let this sink in. Okay, so let's quickly look at the code before we do the example, just to understand how this code is actually different from the code on the previous slide. So we still initialize P as the root. Remember, it's like a linked list. Root is the only entry point. You always start at the root, just like you always start at the head with the linked list. Then, while P is not null, so the condition of the while loop is also the same, we are going to have two cases, the if and the else. The first case is the simplest case. If P does not have a left child, then that's the great success. It's the linear case. We simply print P and move on to its right child. So this if is basically assuming that my tree is one very, very long right branch. Else case is for the nonlinear case. And if the case is nonlinear, in other words, if P does have a left child, then our goal is actually to somehow get rid of that child and make sure we still manage to traverse the tree. Okay, so let's go through the code together with the example just to make sure we know what all of these statements mean. So we initialize P to point to null, to the root. P is obviously not null anymore. We've initialized it, so we enter the while loop. We ask P if it has a left child. And as you can see on my example, D has a left child. Its left child is this node A. So we cannot go into the if, we have to go into the else instead. Let us look at what happens in the else statement. We use a secondary pointer, TMP, and we set TMP to P's left. So TMP will be pointing to A. Then we're going to look for that rightmost node of the left branch. So TMP currently points to the root of the left subtree. Now that we are there, we are going to keep going right as far as we can until TMP right points to null, so until we find that rightmost node, or until TMP right actually points to P. You might wonder when would this blue condition ever be the case, but you will see soon that this will actually happen sometimes because we will be transforming the tree as the process goes along. Okay, so once you've managed to reach either the right equal to null or right equal to P, you're going to check, all right, is my right pointer equal to null? If it is, then I have found my rightmost child. I am now going to transform the tree by doing exactly what we have done on the previous slide. This is a bit of a linearization. We essentially take P and we make it the right child of the TMP. So we make P the right child of the rightmost node of the left subtree of P. Otherwise, however, if TMP right is equal to P, we do something else, and this else statement is what allows us to put the tree back together. But again, let's get to this else when it actually happens. What happens now with our P and TMP? We ask if TMP's right is equal to null. Well, A's right is actually null because it's a leaf node that doesn't have the right children, so we've already arrived at this condition. Therefore, we're going to do this step here. We're going to make P the right child of TMP. So D becomes the right child of A, just like on the previous slide. What is important to note this blue arrow. This arrow actually is the left pointer of D. D still remembers that A is actually its right child. We did not, unlink it in any way. So A's right child is D, but D's left child is still A. They link to each other. And once we have accomplished this, we're going to go to the left child of P. In other words, left child of P is A, so we're going to set P to A. And we repeat the process. We are back at the top of the while loop. We now ask A if it has left children. It doesn't, therefore we're going to print it. Great success, we printed one value. But now we just go right, so P is going to arrive back at D after we have printed A. We now repeat the process. We are again at the top of the while loop. We ask P if it has left children. And in this case, it actually does, right? P's left child is A. So we arrive back at A. However, what are we going to do then? Once we've arrived back at the left branch of P, we are going to say, right, now we want to find the rightmost leaf node, or if we don't find one, perhaps something else will happen. So once you are back at A, you are going to say, okay, I'm at A, I'm going to keep going right until I either find a null pointer or until I find P itself. What are we going to find in this case? A tries to go right. Its right pointer is not null anymore. Instead, it points to P. So we know we have arrived at this second condition right here. So after we've reached this condition, we have to choose between the if and the else. Obviously, the first if does not apply. Team P's right is not null. In fact, it's actually P. Therefore, what we're going to do is we're going to visit P. So we're going to print D. We have already printed A before. Now we're printing D. And then we're going to do something extremely important. We're going to unlink TMP's right. So we are going to set A's right pointer to null. So this guy here, this connection, is going to be deleted. What is the result of that deletion? After we've deleted A's right pointer, now A's right is pointing to null exactly as it used to in the beginning. The tree has actually come back to its original shape, right? We have visited A, we have printed D, and after we have printed D, we have actually managed to not maintain this extraneous link that we have added ourselves. We added, and then also at a later stage, we deleted ourselves. And then we are going to go to the right-hand side of P, so taking us to E, and finally, because E doesn't have left children, we will print it. Great. If this did not make a lot of sense, I suggest you pause the video and simply try to go through this code and look at the pictures that I have provided to make sure that you understand what is going on. But the idea is quite simple, right? You start at a node, you ask if it has left children. If it doesn't, good for you. If it does, go to the left once, then go to the right as far as possible until you either hit null. If you hit null, make your pointer the right child of that null instead. If you do not find null, you will find your pointer instead, and then you have to do the unlinking. So if you find null, you're going to be modifying the tree. If you find P, you're going to be unmodifying it back to its original shape. And like I have promised, let's now do a larger example. This example is actually from the textbook, and once again, I will go through it with you now, but I do strongly suggest that you also go through it yourself, just to make sure that you understand how everything works in this somewhat complex algorithm. And by the way, side note, this is exactly why students sometimes find one too challenging, because we start discovering and discussing these intelligent, complex algorithms, which are non-trivial, but which achieve quite interesting goals. In this case, this traversal might seem cumbersome, but it actually manages to traverse the data structure without adding extra variables to the data structure, and without using an explicit heavy data structure such as a queue or a stack. But anyway, back to our example. So we start at the root, as always. We start at P, we ask P if it has left children. It does. Well, that's a bummer. Remember, we want the tree to be one really, really long right branch, and that's clearly not the case. So let's modify things. Let's try to linearize the tree a little bit. We're going to go left. And after a single left step, we're going to go right as far as possible until we either hit null or we hit P. In this case, we're going to hit null. 7 doesn't have a right child, so 7 is the rightmost node of the left subtree. Therefore, 10 will become the right child of 7. Okay, 10 is the right child of 7, exactly like I have said. But 10 still remembers that 5 is its left child. And that is exactly where we're going to go next. We go to P's left. We're now at 5. We ask 5 the same question. 5, do you have left children? Yes, it does. That's unfortunate. That's something we got to fix. So we're going to go left, and then we're going to go as far to the right as possible. Well, there is no way you can really go. 3 is the end of the journey. 3 doesn't have right children. Therefore, we're going to make 5 the right child of 3. So 5 becomes the right child of 3. So far we haven't printed anything, right? We are just busy linearizing. And then after we have done this, we're going to 5's left, which is still 3, so we arrive at 3. All right, finally we are at 3. P is actually pointing at 3, not to 10 or to 5. It's pointing to the smallest value in the tree. So now is probably the good time to print. But first, we're going to ask 3. Okay, 3, do you have left children? Fortunately, it doesn't. We are finally in the beautiful linear case that we wanted. As you can see, the tree did become one long right branch with a couple of extra links, but hopefully that is something we can, deal with at a later stage. Right, 3 doesn't have left children, so we can finally go ahead and print it. 3 has been printed. Great success. We are now going to move to the right child of 3. We are now at 5. We're going to ask 5 the same question. Have 5, do you have left children? And because 5 still remembers that 3 used to be its left child, the answer will be yes, I do. We are going to go left. And then we're going to go right as far as possible until we either hit null or we find P itself. Right? From 5 we went to 3, and then we're going to go down until we find P itself. So immediately we realize that 3's right child is in fact 5. So what are we going to do? We're going to print 5, and then we are going to unlink 3 and 5. So this connection here that we have added by making 5 the child of 3, this connection is severed and 3 falls back into place. So we've printed 3, we've printed 5, P now points to 7, and we have managed to not totally destroy the tree, hopefully. Okay, we're now at 7. Ask 7 the same question. Do you have left children? It doesn't, so simply print 7 and move to the right hand side. Ask 10 if it has left children. Yes, it does. So you're going to go up, and then you're going to say, okay, great, I am in the left subtree. Let's go right as far as possible until we either hit null or we hit P. You will go one step to the right, second step to the right, and you will discover P right there. This is a signal to print P and unlink. We are going to unlink 7 from 10. You unlink just before P itself, so this is the link that gets severed. And obviously, if that's the link that gets deleted, then 3, 5, and 7, this entire subtree, they are still attached to 10. They basically fall back into place. And you can already see I have managed to, after destroying the tree, I have managed to take it back to its original form. Great, so after we've done that, we're going to move to the right hand side of 10. We're now 20, we ask 20 if it has left children. It does not, thank goodness. So we just print 20. We try to move to the right hand side because 20 doesn't have children. P will become null, and this is the point where you stop the while loop. All right, that is the end of the algorithm. So hopefully this makes sense. Once again, if it doesn't, I suggest you open the textbook. In general, I always advise that you read through the textbook. It might give you a different angle versus what I have discussed in class, but make sure you understand this because obviously all of this is examinable. Great, thank you very much, guys. In the next lecture, we are going to talk about inserting into a binary search tree and deleting from a binary search tree. And we are going to consider those operations for normal BSTs as well as threaded BSTs. Thanks a lot, have a good day further, and I'll see you in the next class.